Greetings everyone. So today we are now going to discuss about group 4A elements. Group 4A elements basically is also known as the carbon family, and that is having four valence electrons. Four valence electrons. Now, if we just look into some general properties of if we just look into some general properties of the carbon family, we will find a lot of different things. Number one is that they have a varied varied general properties such that carbon is a non-metal, silicon is a non-metal, germanium is a metalloid, and tin, lead are metals. So there is a varied general properties, and the metallic characteristics increases down the group as it is usually told. Metallic characteristics. So if we are looking at a few more general properties, we will find that carbon, silicon, and germanium have all of their four valence electrons participating in the bond formation. But if we talk about tin and lead, they have two pairs of electrons. Two pairs of electrons. Um, when one pair of electron is participating, then they form stannous or plumbous compounds, and they form covalent bond. But when they have two pairs of electrons participating, two pairs of electrons participating, then at that point they form stannic or plumbic compounds that are ionic, and then they act as ionic. So this is an important thing. Plumbum has a very important role in paint making, so we are going to look into that as well. All right. So these are some important things, and one more important thing that I would like to highlight over here is that um, carbon is abundantly found in living organisms. Silicon and germanium are abundantly used in electronics. Tin and lead are abundantly used in chemical reactions. Now, let's first talk about the compounds of carbon. There are basically three major compounds of carbon, three major oxides of carbon. Although there are many compounds of carbon, there is an entire organic chemistry based on the study of hydrocarbons. But first, we are going to study the three major oxides of carbon, three major inorganic oxides of carbon. Inorganic. Three major inorganic oxides of carbon. Alright. So first oxide is carbon monoxide. So carbon monoxide, it is a compound in which there are three bonds. In which there are three bonds, a triple bond between carbon and oxygen. One bond, two bond, and three bond. The three bonds between carbon and oxygen, which two of them are the sigma, and one is the sigma bond, and two of them are the pi bonds. And Basically, carbon monoxide is slightly polar. It is slightly polar, and it is a very short, a very small dipole moment, which is of 0.112 dpi. Also, an important point that it is slightly polar. It has a small dipole moment, and it is acidic, slightly acidic. Second one is carbon dioxide. Now, if you talk about carbon dioxide structure is like this. This is carbon in center. This is oxygen on one hand, oxygen on another hand. We have basically this is oxygen. This is oxygen. Now you might see that the structure which is formed is pretty straight. It is a linear structure. It is a linear structure. Let me create the bonds. So here we go with the double bond between carbon and oxygen. One is a sigma, other is pi bond, and basically that creates a linear structure. The angle is 180-degree, and it is a linear structure. Linear structure. Now, if you just talk about carbon dioxide's bond dipole moment, it has zero dipole moment, zero dipole, and it is slightly acidic and non-polar in nature. Non-polar in nature, and it is a bit reactive. A bit reactive. Not generally reactive, but a bit reactive. All right. And third one is carbon suboxide. Carbon suboxide. Now, what is carbon suboxide? It is basically again an unstable compound. It is an unstable compound. Unstable inorganic carbon compound, and that is basically having in this case the valency of oxygen, that basically makes it very similar carbon suboxide, and the valency of oxygen is -1 upon 2. This is an important point considered, and it is same as superoxide. All right, and now let's move on to some compounds of silica. That's an important point because silicon is in a lot of ways similar to carbon, but there are a few things that need to be considered. Number one is the presence of silica in earth. How is silicon found in earth? 25% of the mass of the earth's crust is silica silicon, which is found in the form of silica or silicate. It is found in the form of rock minerals Examples of those rock minerals involve rock crystals, amethy, amethyst quartz, rosy quartz, milky quartz, rock crystals, amethyst quartz, rosy quartz, milky quartz. Rock crystals, amethyst quartz, rosy quartz, milky quartz. And other quartz as well. And silica quartz. Also, these are found in the form of pure sand, which is silicon dioxide, and opal, which is a hydrated variety of this silicon dioxide, as well as sand, which is also an hydrated variety of this. All right. So when it comes to the structure of silicon dioxide, if you just see the structure of silicon dioxide, its structure is a giant structure. Both silicon dioxide and carbon dioxide are exactly same. The only difference between them is silicon is a larger atom, carbon is a smaller atom. It is a larger atom, it is a smaller atom. And because silicon is a larger atom, it causes to form a single bond with oxygen. Single bond with oxygen. But carbon forms double bond with oxygen. Double bond with oxygen. So these are two more important things. Single bond with oxygen, double bond with oxygen. And since silicon forms single bond with oxygen, so it basically is surrounded by, each silicon is basically surrounded by four, each silicon is basically surrounded by four oxygen atoms. Four oxygen atoms. And each oxygen atom is surrounded by four silicon atoms. Each oxygen is surrounded by two silicon atoms. So this is how the entire structure of silicon dioxide works. So why do we mention it as silicon dioxide, even though there are four oxygen atoms and two silicon atoms? This is the entire molecule. This is an entire molecule of silicon dioxide. But why do we call it as uh, SiO2? Because the ratio of silicon to oxygen is 4, ratio of silicon to oxygen is 2 ratio 4, which is simplified to 1 ratio 2, which means The molecular formula is SiO2 and it's a giant structure. So this is about it. And um, there's another important thing that needs to be considered over here, which is about which is that whenever we are going to take silica, let's say I take this silica and I am going to heat it. I'm going to heat it until it fuses. When I'm going to heat it until it fuses, it basically converts into a glassy mass. When I'm going to fuse it or when I'm going to heat it, it will be converted into a glassy mass. That glassy mass, when it is under supercooled, under supercooled, when the glassy mass is under supercooled, that is going to produce a silica glass or vitreous silica. Now, if you just talk about vitreous silica, it has a lot of benefits. Number one benefit is its low thermal expansion, such that it has a very low thermal expansion, due to which it is a good insulator of heat. It is a good insulator of heat, and it has high transparency. It is high transparency, low thermal expansion. It is an insulator of heat, and it is very refractory. It is resistant towards acid attack. It is refractory, which means it does not soften until 1500 to 1600 centigrade, and it is resistant to acids. Resistant to acids and insoluble in water. It is insoluble in water. So these are some important points that need to be considered about vitreous silica. Now there's another important thing. Another important thing, which is this. Another important thing that I'm going to write here is about some important silicates. Number one silicate I'm going to mention is sodium silicate, Na2SiO3. I can also call this as I can also call this as sodium salt of metasilicic acid. So whenever I'm going to take, let's say, sodium hydroxide, and I take let's say sodium hydroxide, and I take silicon dioxide, and I'm going to react them, I'll basically get sodium silicate plus H2O. Second is aluminum silicate. Now, aluminum silicate is a very big formula. Basically, it's something like this. Um, this is basically the formula for ferrald sep ferrald sep K2O dot Al2O3 dot silicon side dot 2H2. It's something like this. This is the entire formula for a rock mineral ferrald sep. Now, when this rock mineral is weathered, when this rock mineral is weathered by chemical action of water, carbon dioxide, by boiling and freezing of water inside the rock, that weathering causes to convert it into potassium carbonate plus sand, which is silicon dioxide, and a clay, and a clay which is known as and a clay which is known as kaolin. Kaolin. So formula for kaolin is Al2O3 dot SiO3. That's the formula. Al2O3 dot SiO3 is the formula. Potassium carbonate, silicon dioxide, Al2O3 dot SiO3, which is known as pure clay, white clay, or kaolin. That's it. That's it. And another important thing about this kaolin. Kaolin is used for making china ware, china ware, and stoneware. So all of these expensive materials are formed with white clays. But there's red clay as well. Red clay basically is made up of several impurities such as iron, calcium, and magnesium atoms, which makes it red colored. When it is heated, it creates a red color because of presence of ferric oxide, which basically undergoes which basically undergoes you know, a combustion due to which causes produce a red color. All right, and right after that we have an other important thing about sodium silicate as well. Sodium silicate basically when it is mixed with any transition metals salt, a transition metal salt solution mixed with sodium silicate, then it causes to produce a beautiful growth like a plant, which is known as a chemical garden. So it can be used for making chemical garden, and that's really beautiful. Chemical garden. And another important thing is it is also known as water glass or soluble glass. Why? Because it is highly soluble in water. It is highly soluble in water, and it is water and in strong, particular strong alkaline solution in water, due to which it is known as water glass or soluble glass. And third thing, which is to be understood, is soapstone or talc. Soapstone or talc, basically, it is. magnesium silicate. Magnesium silicate. It is magnesium silicate. It is magnesium silicate, and physically it is greasy, and is used for making cosmetics. And is used for making cosmetics. And fourth thing to be considered is asbestos. Basically, what asbestos is, it is a hydrated calcium magnesium silicate. Hydrated calcium magnesium silicate. Formula is like this: calcium and then magnesium, two atoms, and then silicate. And this is basically used for making fabrics, incombustible fabrics, and hardboards. While soapstone or talc is made up of magnesium silicate, which is used for magnesium silicate Mg2H2 silicate, and then it is magnesium Mg2H2 SiO3 power 4, and that is used for making cosmetics. It is used for making cosmetics, and it is physically greasy in touch as well. And this reason it is used for making cosmetics. And right after that, we have another important aspect for the compounds of carbon and silica, which is the silicon. Let's understand this as well. So basically, what a silicon is, let me just show you the diagram of silicon as well. Uh, Basically, if you just look at carbon and silicon, both of these are chemically similar. It forms four bonds, and both of them can form a bond with oxygen to form silicon oxide, to form monoxides, to form dioxides. Both of them can form bonds with hydrogens to form silane, methane, just like ethyl alcohol, just like tetraethyl methane. Silicon can also form attach with four ethyl groups. So it is a lot chemically similar with carbon. So basically, silicon, if we just take, let's say if we take this structure of carbon, we take two chlorine atoms attached to it and two methyl groups attached to it. Now, what we actually do is we react this with water. We hydrolyze it basically. We hydrolyze it. We hydrolyze this part. When we hydrolyze this, we basically get the chlorine replaced by OH atoms. Chlorine replaced by OH molecule. And this is a structure we obtain, right? So, uh, when further reacts, this structure, this structure further reacts with its own molecule. When this structure further reacts with its own molecule, it produces a continuous linkage. It produces a continuous linkage with the help of oxygen. In that way, a very long chain is formed. So, if we, so now let's consider this thing. Let's just consider this thing, and we don't need to memorize it. We just need to, understand the concept. Now, what I'm going to do is, instead of the central atom as carbon, I'm going to write over here silicon, silicon here as well, silicon, and silicon here, and then a silicon here. So basically, if the entire scenario is considered in case of a silicon atom as a central atom, then this entire structure, which would be continuous, would be named as silicon. Why do we call this a silicon? Because this entire structure is exactly similar. This entire structure is exactly similar to silica. If you just see the structure of silica, silica has entirely same structure. It's not the it's not a chemical structure of it, it's just the physical structure. But if you just look into the entire structure of silica, silicon dioxide, it will have one oxygen here, one oxygen here, one oxygen here, one oxygen here, one oxygen on the sides and in between as well. But in this structure we are having oxygen atoms joined together with the side chains having the methyl groups, which is known as a silicon, or specifically a methyl silicon. Now, some characteristics of this methyl silicon are such that it is used as a greasing agent. Because it is a methyl group, it is used as a greasing agent, it is used as an oil lubricant, and because it gives an oily base as well, because it gives an oily basis of using it, such that it is having a methyl group, which makes it quite oily and greasy, makes it quite oily and greasy, and it is also used. It is used in hydraulic brakes, and it is used in hydraulic brakes as well as in hydraulic systems because it is having low change in viscosity, such that if we are going to increase the temperature, if we are going to increase the temperature of a petrol by 100 centigrade, then the viscosity would also be decreased by 100 centigrade. But if we are going to increase the temperature of a methyl silicon by 100 centigrade, then it will decrease the temperature, then it will decrease the viscosity by 4 centigrade, by less than 4 centigrade, even by less than 4 times. So in that way it is more beneficial, as well as it is more resistant to reactions as well. Methyl silicon, because it is having methyl group at the end, which produces a steering effect, um, it can even resist chemical reaction at 300 centigrade. At 300 centigrade, no acid formation, no oxidation, no other phenomenal reaction would happen to methyl silicon. And since it is having methyl chains at the end, we can extend that methyl chain by adding a longer hydrocarbon chain, due to which it can act as a synthetic rubber as well. Another important use is that whenever we are going to add whenever we are going to add whenever we are going to have a methyl chain at the end. What is a methyl chain basically in this case? We just see in this is an inorganic part. All of these atoms are inorganic or non-polar. Sorry, inorganic or polar. But this part is non-polar or organic. So what does this mean? This means that it is water repellent. Water repellent. It can repel the water. It can repel the water. So it can also be used as a coating over wires. It can be used as a coating over plastics, and it can also be used as a coating over blotting papers, filter papers, over leather, ceramics, or any other thing that we might imagine to resist water from. And it can also, and because of this, it can also dissolve into glycerol. It can also allow glycerol, right? So this is all about it. Now let's move on to semiconductors. It is a very easy topic. There's nothing much to discuss about. We have already studied what is a photoelectric cell. Photoelectric cell is the one in which we are having a P and N junction, which is separate, which are both separated by a PN junction, a P diode and N diode, and in the middle we are having a barrier, which is the voltage barrier. When the electrons move from P junction to N junction towards electron hole, they basically uh, cross a particular voltage by absorbing the heat energy from the sun, to um, cross the barrier and move towards the N junction, as a result of which it causes to create um, a, a voltage. It causes to create an EMF, which is then you know passed through the electrodes into the battery, and from that electricity is generated. So this is a basic concept of a solar cell or a photoelectric cell. But if we just talk about some semiconductors which are involved in those in the making of those junctions, one of those is germanium, silicon, selenium. These are some metalloids which are used. And secondly, there are certain compounds which are also used as well. For example, silicon carbide is also used. Silicon carbide is also used um, as a semiconductor. Sulfide, lead sulfide, silicon carbide, lead telluride, lead sulfide, silicon carbide, cadmium sulfide, and indium antimonide, gallium halide. All of these, gallium arsenide, are all of these the compounds. Lead sulfide, thallium arsenide, indium antimonide, are all of the examples of semiconductors, and these can be used for making various electronic instruments, transistors, diodes, and rectifiers. All of these can be made with this. Use of lead in paints. Paints is, I mean, like all of the paints. In previous times, what actually used to happen was people used to utilize lead for paints, for making paints. So why did they used to do that? The reason behind it was that lead was a durable metal. It was durable. It had a fast drying speed. It was durable. It had a fast drying speed. Durable, fast drying speed, ability to make various colors. Different compounds of lead can different colors, make different colors with different compounds. With different compounds. And a retarded corrosion. It basically used to retard corrosion. Now let's just dive deep into it. That what specific types of leads were used. Number one type of lead which was used was lead monoxide, also known as litharge or messicot. Lead monoxide, litharge, messicot are the same things. That basically is produces a pale yellow to red color, to reddish yellow color. Pale yellow to a reddish yellow color, which is the lead oxide or litharge or messicot. And that basically is because of the presence of both crystalline forms, rhombic form of lead oxide, which is yellow in color, and the tetragonal form, which is red in color. And second example is lead dioxide. First, before discussing lead dioxide, we need to understand what a red lead is. So basically, what is a red lead? Red lead, also known as minium red lead or tripubum, tripubum, tripalbum tetraoxide. Now, how is it created? Whenever we are going to burn lead in the presence, whenever we are going to burn lead in the presence of oxygen at 340 centigrade, it is going to produce tripalbum tetraoxide. That tripalbum tetraoxide is a reddish brown pigment which can be utilized for various purposes for creating, for using painting over iron and steel to prevent corrosion, as well as for uh, it can be used in manufacturing of lead batteries, lead storage batteries, and it can also be used for the manufacturing of flint glass, glass paper, ceramics, matches. The red part of the matches is made up of this compound as well. and at 470 centigrade it decomposes back it decomposes into lead oxide plus oxygen. Decomposition. Decomposition. Right. And after that we have lead dioxide. So basically whenever we are going to treat um, tri-lead tetraoxide with concentrated nitric acid with concentrated nitric acid concentrated nitric acid, it will produce lead nitrate. It will produce lead nitrate plus lead oxide, lead dioxide actually, and that lead dioxide can be used as a pigment. Basically it can be used for various purposes. It can be used as a pigment, it can be used in ceramics, it can be used in manufacture of lead batteries. So it has a lot of purposes as well. And then we have white lead. What is a white lead? White lead, basically it is a basic lead. It is a basic lead, or specifically speaking it is this PB. This is this. So whenever we are going to, this is basic lead, right? And that basic lead can be treated, can be mixed in in the solution of alkaline, can be mixed in an alkaline solution in order to produce, can be mixed in an alkaline solution in order to produce a red or orange basic lead, which can be used for making the orange or red pigment. And in that way it can be useful. And other uses of white lead can be for the manufacture of for ceramics and other products that can be used industrially. And after that we have the final lead chromate. Lead chromate, also known as chrome yellow. Chrome yellow. Why do we call it a chrome yellow? Because it has a yellowish color, which is often used as a pigment when it is mixed with lead sulfate or barium sulfate, and it can be mixed with some basic solution in order to produce red or orange color, due to which that red or orange color is also used as a pigment. So in that way, these are the pigments that can be used for painting. But nowadays these pigments are not being used because of the environmental problem, as well as because they cause harm to the environment as well. It is lead is a bit toxic as well, which can be harmful for people, due to which most of the time lead paints are avoided in today's era. So that's all about this video. Hopefully we will make another one.